Hello, everybody, and welcome back to the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode 24, where today is a very interesting episode.
Before we start, I want to say that last time
Okay.
we said we'd have a guest on, which is
hmm
not the case
Oh yeah,
because
we did say that.
because there's technical difficulties going on right now, but I'm hoping that very soon it will come to fruition. But
hmm
for now we're just gonna keep doing our thing, just me and Ray. And so we
Yep.
were actually going to record we were going to record an episode of History of Physics, but
Oh yeah.
something came up, and
Something crazy came up. Something crazy.
yeah,
So
we just felt like
yeah, we
this would
had to
be
discuss it.
a nice episode to do.
Absolutely. So a longtime listener of ours goes by the email of Mitchell Clark, probably his name as well. Thank you so much, by the way, Mitchell, for reaching out to us on our email. So he sent us a couple of questions, actually. And we decided this podcast can basically be dedicated to talking about those questions because, believe me, these questions are pretty in detail and we can talk a lot about them.
Yeah, and we know that most, or I don't know about most. Actually, I don't know anything about the people that are listening to this, but I'm thinking that a lot of people who listen to this don't actually have a formal education in math or physics. And so these
hmm
questions will kind of, I think, like most people who don't have that kind of education would be intrigued by these questions as well,
hmm
right? So
hmm
it'd be a good thing
Because,
to
yeah,
to
because in general, once we start talking about the questions, I'm just saying very like realistic questions, like they're not very in depth into physics. So I think when Parker says this is meant for all levels of physics, he literally means it in that way.
Mhm.
Yeah. Okay.
Yeah.
So we can start up with question number one. So he starts the first question with dimensions, and he talks about our dimensions video. Now I forget which episode it was.
That's two.
Episode two. Oh wow, that was
Yeah.
old.
Yeah.
Oh wow. Okay, so in episode two, so he this is his question. In your dimensions episode, you discuss a 2D universe. My question is, why is it in a 2D flat world, the 2D beings would see lines? I understand they have no height and only have a width the 2D observer would see. So while these two-dimensional objects interact or view each other, how is it they see a line with a clearly defined height? If I imagine it as if I were one of these objects and zoomed in on the edge of the other two-dimensional object, would I not be able to measure its height? I mean, I can see it, we interact, so on some physical level, no matter how small, would it not be still be three-dimensional? Or, mathematically, would it be like taking the volume of a cube with one dimension equaling 0? Example, 6 times 6 times 0. And would that not equal 0? Or am I imagining this scenario all wrong?
So one thing I want to say off of the bat is
Yep.
I'm pretty sure the way he's thinking of this is
Mm-hmm.
that a two-dimensional universe is in some way a part of our three-dimensional universe,
Yeah.
which is not the case. You need to imagine that
Mm-hmm.
a two-dimensional universe is just completely separate, and like it has nothing to do with three dimensions, because in three dimensions obviously we have three possible directions to move in, but in two
Mm-hmm.
dimensions there's only two. And
Mm-hmm.
so it's not like a two-dimensional universe is like a piece of paper that we can look at. It's just if you're in a two-dimensional universe, you don't even it's like thinking about a third direction of travel is like imagining a fourth direction of
Yeah.
travel for us. Like
Exactly.
like point in that direction, you can't.
Yeah,
That's it.
exactly, because it doesn't
you,
exist for
you,
us.
you just
For
can't.
us, it literally doesn't exist.
And so when you say that, okay, I understand that they have no height, only a width.
I think the easy way to explain that, actually, I do have a very an easier way to explain that.
Yeah.
Instead of visualizing height and width, which is what you're doing, how about you visualize length and width instead? You visualize a board game. I think that's the easiest thing to think about. The board game is like your 2D universe. Instead of now the only difference between the board game and the real world is that we are not the three-dimensional pieces. Think of us as just two-dimensional shapes on this two-dimensional board. That's, I think, the easier way to think about it, because the moment you think of height, you think of three dimensions.
Yeah.
You can't separate length and width. So if you think of height, you think of three dimensions. That's why it's easier to separate height from the equation and just to visualize length and width. And then you can see, if you do that, even your question where you ask, zoom in on the edge, even that wouldn't work because it doesn't have an edge because there's no height, right? So that question falls apart.
Right. I'm gonna let
basically.
you talk because I know you have lots of things
yeah.
to say. But one thing I want to just get in before is he asks, like, why do two-dimensional beings see lines? Okay, and so this takes kind of like a little bit of perspective. So first, I'll analyze it in 3 dimensions, and then I'll show you how it's analogous to 2 dimensions. Okay, so our eyes are 3-dimensional, right? And they kind of, you can kind of imagine your line of sight as like cones, right? Coming out of your retina. Right? Do you understand what I'm saying, right? Okay.
Yeah.
So it's like cones going out from your retina, and anything that kind of intersects the cone is what you end up seeing, right? But as we know, an intersection of a 3-dimensional shape is 2-dimensional, which means that our 3-dimensional eyes see a 2-dimensional plane. Okay? We don't see in 3 dimensions, because if we were to see in 3 dimensions, that means we would be able to see kind of like every side of a cube at once.
Yeah, that would be very weird.
Yeah.
That would be incredibly weird.
Yeah. So, you know, saying I can see in 3 dimensions, colloquially, it just means like, you know, I'm seeing. I mean, I don't even know if I would ever say that, but in reality, we just see in 2 dimensions, because if you hold a cube in front of you, you can draw what you see and it would look the exact same. So you see on a 2-dimensional plane in your head, right? Now, let's bring it down to 2 dimensions. Now, your eyes are 2-dimensional. And instead of a cone coming out of your eye, it's a triangle that comes out of your eye. And then everything that intersects the line of sight is going to be an intersection of a 2-dimensional triangle. And the intersection of a triangle is just a line, right? So let's say there's a circle. Now let's pretend like we can look down onto a 2-dimensional universe. And then there's you, and then there's a circle in front of you. We can tell that there's an actual circle in front of you, and then you are looking at it. But you have no idea that that is a circle, because all you can see is the width of that circle sitting in front of you. The only way you can actually tell it's a circle is if you walk around it, and you can tell that the width doesn't change, and that's the only way you can tell that, you know, that's the property of a circle, that the radius is equal on in all directions.
Yeah.
Now, bringing this back up to, like, if this confused you a little bit, bringing it back to 3 dimensions, if you have a cube in front of you, but you hold it so that all you can see is one face, okay? You can't tell that that's a cube. You just think it's a square.
It's a square, yeah.
Right? It's only until you walk around the cube that you can tell that it's actually a cube, because of the properties that, you know the cube has, right? So yeah, that's why they would see lines. That's my explanation.
So that's like an intense physics explanation, understanding the physics behind it, and understanding why the 2D people would see lines. Hopefully that made sense. I think that made sense. I think that made perfect sense. Hopefully.
All right. Awesome.
Okay, so now that we've talked the physics behind it, I really want to talk. I mean, I've never done this before, but this is interesting, so I'm going to talk about it. I want to talk about a little bit about the biology behind it. why do we three-dimensional beings see in two dimensions, right? So Parker explained it using the light cone example, using the cone and how light intersects a three-dimensional object, produces a two-dimensional image, which then we see as 2D. However, we can still visualize in 3D. We can still visualize depth. So how does that work? Because our retina at the back of our eye, so our eye is composed of the pupil, our cornea, our essential things in the front, and then our retina in the back. The retina is probably the most important part because it actually captures the image. So our eyes is like a convex lens. Now, what happens in a convex lens? The image gets inverted. So the moment the light from the image hits our eyes, it basically hits the retina. Now, the retina is acting as a screen. A screen, what is a screen? 2D. So basically, the image that is being produced into our eyes are in fact in two dimensions. So the answer to the question, do we see in three dimensions, is literally no, because our eyes cannot see in three dimensions, they see in two. However, because we have two eyes, and there's an angular shift between the eyes, and as Parker said, as we move around it, our brain is basically crazy. Our brain is so smart. So it pieces all of this information together, and it processes the 2D image into a 3D surrounding image, even though it actually isn't. So our brain is doing all the processing around us. But the image, in fact, is in two dimensions that we see. And I think that's a really cool fact about why we see in two dimensions. And that pretty much should answer the question to, in a 2D flat world, will 2D beings see lines? Yes. And the same thing would apply in the three-dimensional world, why we see in two dimensions. Okay. Right. Yeah, so hopefully that question is answered. So what is different in a 2D world? Well, the big thing, right, the first thing is that chemistry would be completely different. Organic chemistry depends on orbital angles. The most basic angle to 120 degrees around the molecule will not be possible because, well, three dimensions are not possible. So the number of orbits, the number of connections, the number of molecules will be significantly reduced. The number of elements will be significantly reduced because molecules won't be able to pack on together. That's a big problem. Another thing is because of this, our neural network in our brain, which also relies on 3D angles, will also fail to work. So we will be a lot dumber. So us figuring out a three-dimensional world in a two-dimensional world is a lot harder than us figuring out a four-dimensional world in a three-dimensional world. Mm-hmm. Does that make sense?
Yeah.
Does that make sense?
Yeah, I think so.
So, stable orbits. How would that work? Would orbits even exist? Right? The problem with two dimensions is that, well, there are no real vectors in any... All the vectors are going to be spanning a 2D plane. So there's nothing that exists for height. Problem with that is that means gravity cannot curve space, right? Because the entire effect of gravity depends on curving space. But if space can't be curved, then gravity just doesn't work, right?
But wouldn't it have the same effect on a two-dimensional universe?
Exactly. That's what I'm coming to. Because it doesn't make sense because gravity wouldn't work with curved space, and in two dimensions there can't be curved space. However, and this is a paper I'm actually going to link in the YouTube description. It's very, very, very interesting. It's called Can Life Exist in 2+1 Dimensions by Dr. James Scargill. Fantastic paper. Basically, he talks about all possibilities in two dimensions. He talks about gravity, he talks about he talks about how we can exist, he talks about how the laws of physics would exist in two dimensions, and he basically goes in very in-depth. So anyways, so what does he say about gravity? He says that gravity itself as a vector quantity will not exist. However, a scalar gravity will exist, and it gives the effect, as Parker said, of bending space. It doesn't actually bend space, but it will give the effect of bending space in two dimensions because scalar gravity exists. Also, a very interesting fact is that stable orbits are actually not possible in higher dimensions because gravity inherently gets weaker the more dimensions we have. So, in 3 dimensions, we know that gravity is inversely proportional to the square of the distance, right? In 4 dimensions, gravity is inversely proportional to the cube of the distance. So, now this is going to be really interesting. You ready?
Yeah.
This is how we know we are in a 3D universe. You know how there's so many theories that, oh, they're 4D universes, like we are in a fifth dimensional, we're in a bigger seventh dimensional universe, stuff like that. Well, no. You know how we know? I'll tell you. Basically, because of this inverse proportionality of gravity, we captured gravity waves in 2016, right? When we captured them, we measured them. We measured the time it took. We measured basically everything we could about them. And the weakening of these gravitational waves were not seen. What was seen is that the gravity was inversely proportional to r squared, proving almost that we live in a 3-dimensional universe. However, now this is where it gets interesting. Higher dimensions can also exist in microscopic realms, like string theory, for example, states
Why do you love string theory?
21 dimensions and 11 dimensions, not talking about bigger dimensions, but microscopic dimensions. And I think that's really cool. So just this entire dimensions question just brings up so much that we can talk about, because I think there's a lot that we didn't discuss in the first episode. And we could have definitely had a dimensions part 2.
Yeah.
So, and anyways, talking about dimensions, another really interesting thing called the holographic principle. So, if you've heard about the holographic principle, you might know how awesome it is, because it is a theory. Obviously, this is like one of the simulation theories of the universe. It's a theory that basically all of us are 2D projections of data. How does that work? So, Hawking radiation in black holes takes place. So, what that does is if any object goes into a black hole, a similar particle, a similar object will be released from the black hole. Why? To conserve energy. It has to conserve energy. If it just goes in the black hole, where did the energy go? Energy has to come out, comes out in forms of Hawking radiation. So, this energy that came out of the black hole is basically the information or the data about the object that went inside. The information, therefore, is preserved. So there was a huge theory going on. I think Brian Greene, you've definitely heard of him. Dr. Brian Greene also, I think it was a documentary where he said that it would be a crazy theory, but it's plausible because of Hawking radiation, where if this can happen near a black hole, why can't it happen all over the universe? So what if all of us, everything in the universe, is basically just data, particles, that are being projected into this 3D world that we are living in? So this is a crazy principle.
Yeah, that's pretty
definitely
cool.
a must read. And yeah. So, okay, let's just go back to your question, because I've been rambling a lot about dimensions. I don't know if I've answered all of your questions.
Yeah, I want to skip forward to question 3 because we already talked a lot about dimensions.
Yeah, but we still have time. Oh, we don't.
No, we don't.
Oh, we really don't. Oh my God, I was really rambling.
Yeah.
I did not notice.
So I'm gonna go to question 3, which is about relativity. So here's the question. Theoretically, imagine if you can travel at the speed of light, the exact same speed, then turning around so you're backwards but still traveling in the same direction but looking in the opposite direction. Now, since we're traveling at the exact same speed of light, would it be complete darkness behind us? And since we are at the limits of what light could move, theoretically, the light behind us would never actually reach our eyes. A simple example would be the sections of a train. Imagine each section of the train is a particle of light, and no section will collide with the one in front or behind it. Okay, so one thing
Interesting.
that is very, very important
Very important.
is that...
I think you're going to mention it. I think I know what you're going to say.
So, you say, okay, theoretically... Actually, no, I'm going to start by saying this. You say, imagine you could travel at the speed of light. Then yes, if you were to look behind you, it would be complete darkness because the light wouldn't be able to reach your eyes. That is right. But here's the thing about living in this universe is that the speed of light is just unattainable. If you want to have mass, if you want to be alive, and I don't even know, like, we don't even have the means to
No,
get
we
to
don't.
that
No,
speed yet.
no, we literally can't because, again, all of our cells have some
Yeah.
components of mass that cannot be reduced to zero
Yeah. Like we
if
can
we were to go at the speed of light.
like humans are able to accelerate protons at very,
Yeah,
very high speeds.
but not ourselves.
But in no way are we able to accelerate like a 1 kilogram block to go
Oh my God, that would be crazy.
99.9 the speed of light. Like that would be absolutely crazy. Okay, so one thing about relativity that's pretty important is that yes, the speed of light is just not attainable. And so
Oh, you're gonna talk.
one thing that you see when you study special relativity is like, let's say I'm moving at half the speed of light forwards and somebody is moving half the speed of light towards me. It's not going to seem as though the person in front of me coming towards me is going at the speed of light because we're going half and half towards each other. That's not the case, because if that were the case, then the entire universe would just collapse. Basically.
That basically, because relative speeds, you can't apply the same equations when you're going at those speeds. That's basically the answer.
Yeah,
Right?
and
Because like everyone still thinks that it's the similar, like two trains, going in the same direction. One's at 100, one's at 90. Oh, they're going at 10 relative to each other. Because we have that idea in our head to just subtract one from the other. But when you're going at speeds close to the speed of light, that entire equation is just wrong. Like you just can't apply that equation. So saying that it will go at twice the speed of light or that we will see each other at the speed of light is just it's just a misconception because that equation just doesn't apply. And another thing about relativity, right, is time. Time.
oh,
Forgot
wait,
about time.
one thing I wanted to say,
Yeah.
um,
Very excited about time.
the thing about the speed of light is that it's literally a constant, which we talked about in episode 3, which is our constants in nature episode. But the speed of light is a constant, which means that let's say we were able to go the speed of light in our frame of reference would still be the speed of light. Okay?
In every frame.
So it's hard to pose, this situation and say that, yes, when you look behind you, you'll see complete darkness. Because that, like, if that were the case, then in your frame of reference, the speed of light would be 0 because it never gets to your eyes. But that's just not like possible.
Yeah.
Like the speed of light is the speed of light no matter how fast you're going. Yeah, that's about it.
Also, a very important thing, also dismissed in question 3. Probably didn't think about it, but again, in your question, you start up with relativity, right? But you miss the important thing about relativity, time, right? Time is also a very important part about relativity. So, what happens as you start going closer to the speed of light? Your time effectively slows down. I mean, you can't see it, but I'm doing a quote unquote. So it slows down, right? So theoretically, this is obviously, as you said, imagine. So theoretically, completely, if we do, or if some particle were to travel at the speed of light, that particle would have no concept of time. So, for example, a photon that gets made at the core of the star of the sun, for example, and takes like, I don't know, hundreds of millions of years to get to the top, right? Because of fusion and stuff. To the photon, it's taken no time at all. It does not even realize, like, it cannot process events. Because
Yeah.
if there's no time, events don't occur. That means one thing doesn't cause anything else. Nothing happens. So if you are traveling at the speed of light, you will not be able to turn around because you don't, like, there are no events that are occurring in your life. So you literally
Yeah.
cannot do anything except travel at the speed of light forever.
Yeah.
That is your only option.
A good way to think about this is that the background microwave radiation, right? At one point, that was light. Okay, it just got redshifted into
Yeah.
microwaves.
Yeah.
It got microwave shifted, but so at one point that was light, and for like the radiation that we detect today, those particles, like since the Big Bang, all the way to now,
Yep.
it seems as if it was less than an instant.
Yeah, I mean, not even. Like, they don't, that's the thing. They can't even record instants.
Yeah.
Like, I don't even think we can think what they would feel like.
No.
Because I think it's just weird. Because how can you imagine no time? Like, what? I don't know how anyone can imagine the concept of zero time.
Here's one thing that I think needs a little bit of clarification. When you said, okay, if you go the speed of light, you can't experience events. Here's kind of how you could imagine that. If you were able to go the speed of light, okay, let's say an event is me waving, okay? So, and let's say you start your journey right before I start, like right in front of my hand, and then when I start waving, you start your journey away from me. Okay, so the moment I start waving, the photons, that your eyes would perceive from my hand would just be, forever chasing your state of light speed
No, but
velocity.
again, no. But again, remember when you just said that
I know, I'm
when
not
I
talking
start,
about.
you start? Like, I don't choose when to start. That's what
No,
I'm saying.
but this is
If I'm
just.
at the speed of light, I'm always traveling at the
No,
speed
this
of
is an
light.
example though. I'm just saying, like, let's say you were a photon, but
Okay.
the information, like photons carry information, right? Because
Yeah.
that's how we
Yeah.
see. Okay, so everything that happens, imagine it's like a waiting line of just photons that are all traveling like in a block, right?
Hmm.
Certain intersections of that block will carry information based on what's happening. But if you're just in that line, continuously just moving along, you will never experience what happened right before or after you. You're just gonna stay in place in this whole block of just I don't know. I don't know, to be honest. Did that make sense? I don't know.
Well, hopefully that did. So can we finish the two questions or?
There's only one left. I mean, well, I guess. Do you want to do number 4?
Okay, so question 4, special relativity and quantum entanglement. Oh, wow. This is just more of a neat idea than anything practical. Imagine having a hypothetical camera with a lens that can zoom unbelievably deep into space. Now, also imagine it is also completely controlled by quantum mechanics, meaning that it can take and send images across space instantly, faster than light. In this hypothetical scenario, we could launch this camera deep into space through a wormhole. So now we just transported the camera through space, potentially millions of light years away. But because the images it sends are using quantum mechanics, it sends instantly. Therefore, you could potentially view the Earth from millions of light years away in real time from across the universe. You would essentially be looking back in time at an Earth we don't yet exist on. Pretty cool to think about. Although extremely hypothetical, furthermore, you could then send the space camera from its journey millions of light years away towards the Earth at near the speed of light, and the images it would send back of the Earth would be of it aging extremely quickly until the camera reached Earth, in which case time would be the present time.
That's pretty
Wow,
cool.
that's
Yeah,
a cool idea. That's a cool idea.
it's cool to think about. And, like, of course, if we had the technology in like the quantum
Yeah,
computers
it would
and
be cool.
the ability to manipulate wormholes or at least just use them if we find one, and also have the ability to accelerate a camera towards the Earth near the speed of light while simultaneously taking pictures and sending them through these
No, but
quantum
anyways, I mean, this
computers.
is the completely hypothetical. But I'm just saying, do you? No, no. I think what he's asking is like, would the physics work? I think that's what he's mainly saying. Like, would entanglement? Yeah, I mean,
I'm not
it would,
qualified
right?
to answer this
I
question,
don't think
but
either of us are, to be
I think
honest.
it's
But like,
possible.
whatever I mean, whatever knowledge I have on the matter, which could be wrong to be honest, but whatever knowledge I have, because quantum entanglement is a very, specific subject, it requires a lot of knowledge that I don't think either of us have at this moment.
Nope.
But what we can answer right now, at least I think, is it makes sense. Because see, if particles are entangled, right? So basically entangled are like entangle is a fancy way of saying they're sent towards each other, because if they're sent towards each other, they literally entangle themselves. Like that's the process of entanglement. So, if you do that, right? If you entangle these particles and then you send these particles millions of light years away, hypothetically, yes, if it does take images, you should be like, I mean, okay, I don't really know how it would
I
send
think this is
images,
how it would work, okay? So
but yeah,
let's say
okay.
you take an image and then like how does it work? Let's say every
Like the
electron.
spins would change. The
Yeah.
spins would change.
Okay, so let's say one spin would correspond to a black pixel and the other would correspond to a white pixel. And then you just have a whole bunch of these black and white pixels that when it takes the picture, of course the picture would be in black and white, but if you just have a lot of pixels, it'll be pretty detailed. And then
But
of
also
course
we
you can
have to
use
somehow replicate the image captured onto these particles. Nah, I think actually that's possible.
well,
I
if you
think that's very
just
possible.
you just relate the spin to a 1 or a
Yeah,
0.
to a one. Yeah, that's
Yeah.
very possible.
And so of course you can use like processing technology to apply color to these images. It wouldn't have anything to do with the actual quantum computing because I think that would be much.
I think yeah.
I mean,
I think color would just be more particles, no?
actually that it might not be that much of a stretch. Like you can just have a string of particles and
Yeah.
each string corresponds to a color and then
I mean, if
have
they
yeah.
already are doing black and white, why don't
Yeah.
they just do color?
Yeah, I
Like,
guess.
if we're already so advanced, I'm pretty sure we can just do color, bro.
Yeah, yeah. I guess you're right. But
Okay,
I mean,
so yeah, sorry, continue.
yeah, I mean everything. If we had the technology, I would say yes. It's
I would
possible.
say it would be so cool. It would be so
Yeah,
cool
that would be
to
really
try
cool.
that out. I mean, that would be really interesting. I would love to see it work, but
Yeah, we could
yeah,
find out so much crazy stuff about like the history of the Earth,
yeah.
like
The,
super crazy
there's
stuff.
some cool things. Yeah, we could really find out some dope stuff. Okay, so I think we can maybe extend this episode a bit and just answer the last question, because I don't want to like make a whole new episode for one question.
Yeah,
And you can also cut these parts off where we're talking, so it's gonna become shorter, right?
yeah,
Okay. So question 2 sounds good.
yeah.
But okay, so now we're gonna answer the last question. Kind of gone haywire, but now we're on question 2.
She's gonna
That
be
is also
brief.
sorry. Oh yeah. By the way, I forgot to mention one really cool fact. On the first question, if we were two-dimensional beings, two-dimensional shapes, we would have to poo from where we eat, literally, because if we had a digestive tract from the mouth to the anus, it would literally split us in half. And I think that would be, and I think that's pretty funny. That it's a cool fact about 2D creatures. Anyways, so
Congrats.
question 2. You also briefly dimensions. You also briefly discussed the fact that we have multiple dimensions and that typically people will refer to time being the fourth dimension. But according to space-time, time and space are one and the same. And without one, you essentially don't have the other. So my personal theory or belief is that time must be considered one of the first, if not the first, of the dimensions. A simple example would be, again, our flat two-dimensional world. If it only has two dimensions, one for width and one for length, how can it exist in time if time is the fourth dimension? Or am I missing something?
I think you are
You are,
missing
in fact,
something.
missing something.
Yeah.
Yes.
Okay, you say a simple example is a flat 2D world. How can time
Mm,
exist? Well, think about it like this. How can time exist in a three-dimensional world? You know,
exactly.
it's
I
it's
mean,
it has nothing to
okay,
do
yeah.
with
Mm,
where you classify each dimension. Like you say, oh,
yeah.
time is
I was
the fourth dimension.
Yeah, it doesn't
Therefore,
have to be the fourth for all of them. Like in the second dimension, in 2D, it
yeah,
can be the third dimension,
it
you know?
can it time just exists.
Yeah.
Like it just exists. So
Like to be honest, it can totally be the first dimension in our world too. It's just that we don't really use that because we first talk about spatial dimensions and then talk about time.
right.
But again, that is in like the Euclidean way of thinking about space as like space and time separately. But yeah, you mentioned space time, which is the Minkowski version of space time. It's how you view space as space time being literally an axis itself and not separate. So they're just different ways to view the universe. It's not like it's wrong or right. It's just different ways to view it. You know?
Hmm. Yeah, I think.
Yeah.
I mean, I think that's about it. I don't really have anything else to say about that.
Mm, let's see. Can we? Yeah. So basically, the problem with question two is that I think you just have a misconception of like space and. I mean, again, it can be space and time separate. It can be space time. Space time is generally how we view it in reality. But when we're doing, like just simple mathematical calculations, like about position and stuff, we don't really need time. So why include it when we don't really need it, right? So
Right.
in those scenarios, we can use them separately. So again, it's all just personal preference. So again, is that time must be considered one of the first dimensions? Doesn't really matter. Again, it's just convention. It's just how we use it. We usually talk about our first three spatial dimensions: latitude, longitude, altitude, and then we talk about time. That's just how it's been for millions of years. So that's
Millions of
basically it.
years. All right.
Okay, so hopefully, Mitchell, that answered your questions. Thank you again so much for emailing us. And again, if anyone wants to email us, feel free to. We'll include your questions in maybe one of these next time.
Yeah, so make
Yeah.
sure to follow the podcast wherever you're listening. And
We have an
also,
Instagram page now too.
oh yeah, true, we just made
Yep.
that. It's
Yep.
at math.physics.podcast
It's
on
pretty cool.
Instagram. We also have a
Yep.
Facebook page, but I don't
Oh,
really,
we do?
yeah, I
Oh,
don't really use
I
it though.
I didn't know that.
We have like automatic posts. Every time we post a podcast, there's like an automatic thing that goes out on
Oh,
Facebook.
is it from our podcast account?
Yeah, but
Okay.
I mean, I don't really use it. If you want to go follow it,
Uh,
I mean, you're free to do so. It's just Math and Physics
Absolutely, go for
Podcast.
it. Yep. I
So
mean, Instagram is where we're gonna be posting all our like live updates. If we're,
yeah,
if we reach 5K downloads, new episode, anything like that, we're gonna be putting it on there. So if you want to follow it, that would be awesome.
yeah.
Yep.
So
So,
yeah, this has been the Math and Physics Podcast. I am your host, Parker.
and I'm Ray, and we will see you soon.
See ya.